Okay, we're going to get back to section 4.5, and we're talking about analyzing the graph of a function, and we're just kind of going through the list of steps here to be able to sketch a curve. Okay, and so I was going to show you another example in this video. So we'll get right to it. Suppose that we want to graph f of x equal x times the square root of 2 minus x squared using the list of 10 steps there. Okay. Well, step one is to state the domain of the function. So the domain, of course, I don't want a negative underneath the square root sign, and we're not doing anything with I or imaginary numbers. And so I'd want to set the what's underneath the square root to be greater than or equal to 0, and then solve for x. Well, if I do that, I got x squared less than or equal to 2, take the square root of both sides, and that means that x has to be between negative root 2 and positive root 2. That step 2 would be getting the intercepts. So to get the x-intercepts, I'm going to let the function be 0 and solve for x. If I set each of these expressions equal to 0, I'm going to have x equals 0, and then the square root of 2 minus x squared equals 0 means that 2 minus x squared equals 0. Add x squared to both sides. X squared equal 2 means that x would be plus or minus root 2. Okay, the y-intercepts, I got to plug 0 into the function, and I would get 0 in return. So these 3 points here would be my 3 intercepts. Now, by the way, these 2 points are the end points on this interval here. Okay, for this function, I will have a start-stop thing going. Okay, okay, so now we're on step 3. We want to see if there's any symmetry with the graph. So now f of negative x and negative f of x are going to be the same, which would indicate that f is an odd function. Okay, and an odd function is always symmetric to the origin. If I replace x with a negative x squared is the same as x squared, right? And I'd have a negative x in front here. Well, that's going to be the same result that I would get if I just throw a negative in front of the expression, right? So because those expressions would be exactly the same, f would be symmetric to the origin. Now, symmetric to the origin just means that any point that you plot, x, y, negative x, negative y is also going to be on the graph. Okay, so that can be helpful here, and when I draw this, I can consider any symmetry that, or know that the graph is symmetric here and use that. Step 4 is computing all the infinite limits and limits at infinity. Okay, now in the function, we didn't have any division by 0 going on, right? So we haven't thrown away any numbers that would create vertical asymptotes on the graph. And if you have infinite limits, you're going to have asymptotes at those spots. We don't have that here. Okay, and now also, there wouldn't be any limits at infinity to compute since x is ranging from negative root 2 to positive root 2. There is a start-stop thing going here. Okay, x is not heading out towards infinity or negative infinity. So there would be none of those to compute. Okay, these 2 intercepts, as I mentioned before, are the endpoints of the graph. There's no asymptotes on the graph, and so we can go right to step 6 now. Step 6 is to compute the first derivative and find the critical numbers. Well, let's see. When I do that, I'm going to have a product rule, and within the product rule, I'm going to be using the chain rule. All right, so let me differentiate here. I got the first is x times the derivative of the second. That would be a chain rule. You're going to have 1/2 times 2 minus x squared to the negative 1/2 times the derivative of 2 minus x squared. That's negative 2x. Okay, and so first times derivative of the second plus the second is the square root of 2 minus x squared times the derivative of the first is x. The 2's will cancel there. X times negative x is negative x squared, and I've rewritten this in a radical form. Let me combine this to a single fraction now. Okay, and so I've got the square root of 2 minus x squared times the square root of 2 minus x squared. That would be 2 minus x squared. The square root of 2 minus x squared would be in the denominator there, right? And can combine these first and last terms. And when you set this equal to 0 and multiply both sides by the denominator, that will get rid of the fraction that we see on the left. Negative 2x squared plus 2 equals 0. If you subtract 2 and divide by negative 2, you'll have x squared equal 1, or x would be plus or minus 1 when you take the square root of both sides. Okay, so those would be two critical numbers. Now actually, root 2 and negative root 2 would be critical numbers as well, since those two numbers cause a problem for f prime in the denominator there. And those two numbers are in the domain of the function, right? Now, when I use the first derivative test in the next step, I would be starting at negative root 2 and ending at negative root 2 anyway, okay, because, that's the condition on x that we've already stated. So, but those two numbers are technically critical numbers. So in all, I have 4 critical numbers that are going to split the table into 3 sections, okay? And I've got my intervals arranged here, and I'm going to choose numbers in the interval, find the values of f prime, and then state the conclusion. So for the first group, and by the way, root 2 is roughly about 1.4 if you were to go nearest one digit on that. So in the first interval, I need to select a number that is between negative 1.4 and negative 1. Negative 1.25 would be a good one to use, or negative 5/4. And if I plug that into the derivative, negative 5/4 squared would be 25 over 16, times negative 2 is negative 25 over 8, plus 2. 2 is the same as 16 over 8, right? So I've got negative 25 over 8 plus 16 over 8. That would be negative 9 over 8, or negative 1. And by the way, in the denominator, of course, I'll always have a positive there, right, under the conditions for x, because we know anything coming out of the square root sign is never going to be a negative. So I'm going to have a negative in the numerator, negative 9 over 8, divided by some positive, and the decimal that I was getting is roughly negative 1.7 if you were to go to the calculator and check that. And the fact that that's a negative means that we're decreasing on that part of the graph. Okay, and the next interval, 0, is between negative 1 and 1. Okay, if I plug in 0 into f prime, I'm going to have 2 divided by root 2. That's a positive number, so I'll be increasing on that part of the graph. And then for the last interval, we need a number between 1 and 1.4. 1.25 would be a good number to use, or 5/4. And if I plug in that number, I'll get the same output as I did when it was negative 5/4, right? Because negative 5/4 squared is the same as 5/4 squared. I'm squaring x here. So it looks like I'm getting negative 1.7, again, if you were to go to the calculator and check that. So we're back decreasing again. Okay, we're decreasing and then increasing. That means that we're going to have a local min at x equal 1. And when x is negative 1, and you plug that into the function, you're going to have negative 1 times the square root of 1 is 1. Negative 1 times 1 is negative 1. Okay, and then we're increasing and then decreasing. That's going to produce a max at x equal 1. When x is 1 and you plug that into the function, 1 times 1 is 1. Okay, and let's see, the next thing then, we're on step 8. We need to find f double prime. F double prime is going to be a quotient rule. And within the quotient rule, I'm going to use the chain rule when I differentiate the denominator. Okay, so let me do that now. We got the bottom. It times the derivative of the top is negative 4x, and then minus the top times the derivative of the bottom. That'd be a chain rule. We're going to have 1/2 times 2 minus x squared to the negative 1/2 times the derivative of 2 minus x squared is negative 2x. The 2's will cancel there, and this is all over the denominator squared. The square root of 2 minus x squared squared would be 2 minus x squared. And okay, so I've pulled this term in front. Negative, let's see here. I've canceled the 2's, like I said, and distributed the negative x into these two terms. So I'm going to have 2x cubed minus 2x, and I've rewritten this part into a radical form. Let me go ahead and get a single fraction in the denominator. I'll cross multiply here. You got the square root of 2 minus x squared times the square root of 2 minus x squared. That'd be 2 minus x squared. And I've got my single fraction. And now 2 minus x squared is the same as 2 minus x squared over 1 in the denominator. So let me go ahead and flip that. The square root of 2 minus x squared times 2 minus x squared, keep the base and add the powers, that'd be 2 minus x squared to the 3/2 power, right? When I take 1/2 plus 1 is 3/2. Now up here, let me combine my like terms. We're going to have, let's see, 4x cubed minus 2x cubed is 2x cubed, and then negative 8x plus 2x is minus 6x. 2x is in common to these two terms. You can factor that out. And now I'm going to set that equal to the expression equal to 0. Okay, multiply both sides by the denominator. That way you get rid of the fractional form there. And then you can set 2x equals 0 means that x is 0. X squared minus 3 equals 0 means that x would be plus or minus root 3. Now these two numbers are not in the domain of the function. Okay, and so I would not consider those any further in the calculation here. We're going to only have one number to use in the table, and of course, with the conditions that we do have for x, I'd want to include endpoints here. I wouldn't want to blindly have arrows on either end, right? X is not going to infinity and negative infinity. So I've created my two intervals, and I can select my test values here. I'm using the concavity test. So a number in the first group, let's see, between negative 1.4 and 0, we can use negative 1 and plug that into f double prime. Okay, if x is negative 1, you're going to have negative 2 times negative 2 is 4, divided by 2 minus 1 is 1, 1 to any power is 1. Okay, so 4 over 1 is 4. We're concave up on that part of the graph then. And then in the next interval, we need a number between 0 and 1.4. 1 would be a good number. And if we plug in 1, let's see, I think the only adjustment here is we're going to have 2 times negative 2 is negative 4. I'm still dividing by 1. So negative 4 would be the value of f double prime. We're going to be concave down on that part of the graph. All right, I switch concavity from concave up to concave down at 0, and therefore I'm going to have an inflection point when x is 0. When x is 0, y is 0. We've already said that. So this intercept here that I've mentioned back in step 2 is also an inflection point. Okay, and now I think I'm ready to go ahead and draw this. I've got my axes set up here, and just kind of run through the information again. Here's the domain of f. I've got 3 points I know are on the graph. Again, root 2 is roughly about 1.4 if you were to check that. Okay, so here's root 2 is 0, here's negative root 2 is 0, and then 0, 0. Okay, no asymptotes to worry about. We do have a local max at 1, 1, so I've plotted that point. There'd be a hill on the graph. And we've got a local min at negative 1, negative 1. I've plotted that point. Okay. We are concave up on the interval negative root 2 to 0. So tangent lines to the curve are all going to be below the graph. Of course, that'll create this local min here. And then we're concave down from 0 to root 2. Okay, and so all the tangent lines are going to be above the curve. And of course, that's going to create a local max right here at this point. Okay, and so here would be a sketch of the graph of f of x then.